Since we've been focusing on solubility rules and the use of NAGSAG, a further exception is that no ionic compound is completely insoluble in water. In fact, an ultra small amount of the ionic compound actually dissolves before it reaches saturation, and at this point, equilibrium is reached, in which the rate at which the ionic lattice is breaking away is the same rate at which it is being reformed. So the word insoluble is a relative term, in which having a solubility of less than 1 gram per liter. For example, when describing the solubility of calcium hydroxide, an equilibrium exists between its lattice and its aqueous states. We tend to write the reactant as solid and the products as the aqueous forms. Because it's an equilibrium reaction, a double arrow is used and we can determine the equilibrium constant for it. But instead of calling it the equilibrium constant, we refer to it as the solubility product, KSP. Same rules apply, just as with the equilibrium constant, in which we only include concentrations that can actually change when reaching equilibrium. Therefore, the KSP for calcium hydroxide is like so, since the concentration of solids don't actually change. Equilibrium systems only occur for sparingly soluble and insoluble salts, since completely soluble compounds aren't really equilibrium reactions. So let's calculate some solubility products. Shout out to Chemistry in Focus for this question. The molar solubility of calcium phosphate is 0.002 grams per 100 grams of water at 25 degrees Celsius. Calculate solubility product. Okay, so just like the usual equilibrium expressions, concentrations are taken at equilibrium, so we'll assume that this has happened here. First, we write the balanced equation. Also, concentrations are measured in moles per liter, so we have to convert this into that. So logically, 0.002 grams over 0.1 liter will give us 0.02 grams per liter. That is, how many grams of calcium phosphate we would need in a liter of solution. Then we convert grams into moles using moles and mole mass, giving us 6.45 times 10 to the negative 5 moles. And since we converted the mass from grams per 100 grams into grams per 1000 grams, we now have the concentration of calcium phosphate at equilibrium. So the calcium ion concentration will need to be multiplied by 3, because for every 1 mole of calcium phosphate, 3 moles of calcium ions are produced at equilibrium. The phosphate ion concentration will need to be multiplied by 2, because for every 1 mole of calcium phosphate, 2 moles of phosphate ions are produced at equilibrium. So now that we have these values, we can write the KSP expression, remembering that concentrations are raised to the power of their coefficients. Plug in the values, get the results, check the sig figs. Now this tiny number tells us that very little amounts of calcium phosphate actually dissociate in water. So this video is getting a little lengthy, so more examples will be done on another video.